All right, so let's take a look at graphs of exponential functions and talk about the comparisons and this idea of inverses. So to start us off in this discussion, let's just establish and remind ourselves that this is in blue our exponential, and then in pink or red, that's our log function. Exponential functions and log functions are inverses of each other, and that means that if they're inverses, then they are symmetrical over this line y equals x. They have symmetry over this line. So symmetry meaning a direct reflection of the lines. We have also here, just to look at and discuss, we have the natural, or the e function, which is exponential still. And then we have the natural log, which in this case here, what we want to make this relationship, and I haven't brought this up yet, is that if you have a normal base like 10, or 2 to the x, or 10 to the x, or 5 to the x, then when you do that, you're going to use log base 2. Or in this case here, it'll be log base 10. Or right here, it will be log base 5. And obviously there's more to that, but that's base 2, base 2, base 10, etc., etc. When you have an e, and this, you saw me say something about this earlier, when we have e to the x, we don't use logarithms. So we don't write that as log e, okay? We use what's called a natural log, so it's ln. And then remember that the e is understood. Just like right here, this 10 is actually understood, so technically we would just have written log on that one, and that would be understood to be a 10 right there. So with the ln, it's the same thing. The e is understood. So when you grab this calculator and you mash ln, there's an e right there. It's just understood. Just like if you mash log, there's a 10 right there. It's understood. But if you need a different base, remember that's where you're going to need to go use that math, go to log base right there and choose that, so that way you can type in the base that you're trying to solve with. All right? So graphs and a little bit about bases and natural logs and stuff on that slide. All right, so we move on, just a couple of visualizations, you know, like you can see they're symmetrical, so no matter what your base is, they're going to be symmetrical. So here we are, and on this slide right here, what I want to talk about is just the whole idea of parent function again, and utilize this concept, you know, that when we have an exponential function is going to cruise along like this, it's going to turn the corner, and it's going to climb very quickly. Okay, there's going to be this line of symmetry. So let me change this around just a little bit real quick, and we'll make it black. Oops, that's a good thickness. Let's do that. Just palette, make it black. And so, you know, you're going to have this line of symmetry that these things go through there, so they're symmetrical. Remember that this is the parent function of the exponential, so this is y equals b to the x. This is the parent function of the log function, which is, which is y equals log base b of x. Now notice the x and the y's have changed, unlike our other conversions, because we actually found the inverses of each other. So remember, to find the inverses, you switch the x and the y's and you solve. So here we can see the x, y's have switched. So what do we want to discuss here? Well, what we want to see on this particular slide is that on an exponential function, the domain was all real numbers. On an exponential function, the range was from 0 to infinity. And on an exponential function, I had an asymptote at y equals 0. And remember, there was a correlation between this 0 and that 0 right there, right? So now we go to log functions. And in log functions, what we want to see is that the domain and the range. Well, if things are inverse of each other, that means the x and the y's is switched. So in this case here, my range will be negative infinity to positive infinity, because this graph turns the corner and it goes down for evers and evers and evers towards negative infinity. And even though this graph, as it comes up, is going up, it's going out a lot faster, it's also going up. It's gradually going up, 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 up. So it's also going towards positive infinity as it increases out this way. When we talk about the domain, however, our domain swaps with our range in our exponential. So our domain is 0 to infinity. You can see here on the graph. Here's x equals 0. I'm never going to go across 0. That means that I have an asymptote. My asymptote is at x equals 0. So once again, there's a correlation between that and that right there. The key thing about this slide is that I want you to see the relationship is that these guys are inverses of each other. And if two functions are inverses, that means their x and y's are going to switch. Their domain becomes their range, the range becomes the domain, the asymptotes switch values. All right, so now this rule will apply for all logarithmic functions. So as we move forward and we take a look at this first slide here, and we want to, nope, we're going to skip over that one. Okay, we want to look at this guy right here. We can clearly see that we have the same relationship that we had from previous situations, and that is that if we have a number on the outside, not inside the parentheses, whether it be a positive or negative, we have a vertical translation or a vertical shift. And so what we're going to go off is the parent function. So our parent function is going to have that basic shape that we discussed in this slide right here. And so we have our parent function, and we're just going to take that parent function, we're going to move it up 7 times. So now, the way that we're actually going to do this is, I'm going to demonstrate here in just a minute, is that we're just going to use the translation concept. We're just going to choose the type of graph and talk about the translation. Then you'll have to tell me about the domain and the range. So let's take a look at another one. Same concept here, but now you can see that my C value, in this case we're calling it C instead of H, is inside the parentheses. That means that I have to have a shift to the right, because it's -3, which will move it to the right 3. So you can see our parent function would transform over 3 times. So now, what does this look like inside the homework? That's kind of the key question, right? So let's open this up in our homework, and let's see what we get. So let's go find us a question here. Okay, so here's one like the first one. So same deal. You click on this guy, make it larger. You choose your graph first. So if you hover, once again, it'll tell you exponential, but we're graphing log functions this time. So that's my log function. You just click someplace on the graph. At this point, you can see that your transformation tools pop up. We don't have to change anything on this graph. We don't plot ordered pairs. We just know that because of that +5 on the end, that it's not a vertical stretch, it's not a horizontal stretch, it's a vertical shift up 5 times. We slide that guy over to 5, we let go. Now, one other thing about this problem is that I believe they ask us, nope, not on this one. So that's all we need. We hit save, check answer, good job. Now they ask us for the domain. Okay, well, we've got in our notes, we talked about on this parent function here that my domain will come from my asymptote, right? So wherever you see your asymptote, that's where your domain is going to start. So we come back to the problem, we look at it, and to me, I see that this guy never crosses 0. So if I make that bigger again, this graph is never going to go across x equals 0. That means my asymptote's at 0. That means my domain would start at 0. So 0. And there we go. All right, my range. Well, we talked about here that logarithmic functions, my range will always be from -infinity to +infinity. Okay, and you continue on like that with those problems. So here's one, just identifying the graph. So now that's another vertical shift. So here we go, here's one that's a horizontal. So same process, you click that guy, we choose the tool, we click on the graph. Now there is a slight difference in this problem here, and I'm glad we did this one, is that we have a horizontal shift. -7 is to the left, but since it's inside the parentheses, we move it to the right. So this would be a horizontal shift 7 times. We click save. Okay, I forgot to do something here, so let's go back to the graph. it says in the directions, it says graph the function and then graph the asymptote as a dashed line. So now that I have my function drawn, now I have to grab my line tool, grab my dashed line tool, and come here and draw my asymptote. It takes 2 points to make an asymptote. I click save, I check my answer, and there we go. So if you don't put that asymptote on there, it's not going to give you the correct answer. So you want to make sure you do that. Our asymptote, well, we move this thing over 7 times, right? So my asymptote is at +7. It asks you for the domain and range again. So in this case here, remember my asymptote ties in with my domain. So I go from 7 to infinity. And my range, we talked about, in this case here, will always be all real numbers. But if you look at your graph, you should be able to see that. You should be able to see that you go from -infinity, and I'll use my arrows here in just a minute to show you what I'm talking about. Okay, so you can see here that this graph comes down and it turns the corner and it goes forever. So you keep on going down, 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 all the way to -infinity. And then on the other end of the spectrum, it turns the corner. And even though it's going out really quickly, it's also coming up ever so gradually. So over time, it will continue to go. It'll take it a long time to get to infinity, but it'll still go to infinity. All right, so that wraps up this particular video. I think we got one more little piece after this, but this will help you with the graphing using the transformations.